Okay, morning everybody. So I think my job is to let the coffee head down into your systems before we get our keynote for the day up. So what I'm going to do today is talk a little bit about ARM research, give you some background of how we work, areas that we're interested in, and how you might reach out and work with us. So before I get onto ARM research, I'll give you a bit of background history of ARM and our business model. And this chart looks like every gadget that I've ever bought and sometimes regretted, except for the HPC installation that Jonathan put in last night. Haven't bought one of those. But to head back to the beginning of ARM, we started out as a joint venture between Acorn Computers, that was a UK-based computer manufacturer back in the day, back in the 80s and 90s, and Apple. And at the time, Acorn were looking for a replacement processor for their BBC home computer, which I think was the 6802. And Apple were looking for a high-performance or low-energy implementation to go in their Newton PDA. I never owned a BBC, but after I joined ARM around 94, I think, a group of us in the room in the CPU design team, instead of taking our payday packet to buy a meal out at the end of the month, we saw a special offer. I didn't get a corporate discount from Apple, but we saw a vendor in a technology rag, made a joint purchase, and Apple Newtons came along, and they were awesome. So they had digitized a pen tablet, handwriting recognition that worked enough to persuade you to try and make it work, but not fully successfully. So one thing I remember from that picture is, so amongst the kind of open plan group of engineers in the room, there were two Simons, and one Simon was a bit geeky, a little bit like me, so we purchased a Apple Newton, and we're very pleased with that. The other Simon was more interested in cars, and he'd been through a sequence of relatively bad taste European sporty cars, and he saved up his money instead, got a Fiat with nice bulbous headlights, bright yellow, and it had V6 on the side. Anyway, so one Simon's now left, the one who bought the Newton, and he works in the record industry, and the other Simon is a CEO. So from that message, I'd say if you want to channel your geek, you might end up on the stage a bit like this, and if you want to lead ARM, yeah, you need to focus more on petrolhead interests. Anywho, so the process design for the Archimedes for Acorn and Newton happened to have some characteristics which made it really excellent for the emerging GSM phones, and that kind of sealed our success going forward. And now it's pretty hard to look at any device and not see ARM technology contained within. What some people aren't familiar with is we don't sell any hardware, so although there are ARM technologies in all of the devices on that page, we actually just deliver the intellectual property to our partners, and they incorporate their own IP blocks and create specific system on chips targeting their market niche. So the business model there is we deliver design materials. Back in the day, it's kind of GDS2 layout. Nowadays, more like RTL, soft IP. We get a license fee for that, and we also get royalties for each part shipped. Now, about 2 years ago, Massa from SoftBank decided to purchase the company. Great move, and take us off the stock market. So there were two things converging about that point in time. So this slide probably focuses still on giving an image of a mobile phone and some of the IP components in there. We're interested in other areas, automotive, industrial, and infrastructure. But about 2 years ago, there were two things going off there. So one, the activity of being taken off the stock market meant we could reinvest our profits to grow more quickly. We do still need to make a profit, so loss is not an option. And the other thing that was happening at the time was a group that largely originated in ARM research that was looking at kind of IoT services and software, had actually sprung out as a separate new business. And that looks like, to ARM at least, an area where there's huge growth potential. So we believe we're going to get to large numbers of IoT devices, whether it's trillions or less than that, doesn't really matter. The scale of the problem is big enough that there are huge challenges in the connectivity, the management, and the data that you're collecting from it. So I think the message really from this slide is ARM now is two companies. There's a hardware IP facing one, and there's a software services facing business. And that kind of cements the focus of ARM research internally. We are a grounded research organization, so we don't get free rein to look at anything that we find interesting. We generally get measured on, so which business group did you deliver technology solutions to? So with that, I'll talk a bit more now about ARM research. Probably comprised of two major components. So one is the internal research programs, so the blue box, and that's more what you might expect as a team of engineers who are tasked with running projects internally, identifying technology gaps, problems, and hopefully solutions that if they get delivered are going to be beneficial to the product groups going forward. So that's an internal facing function. There's then a set of three more external facing ones, collaboration, enablement, and education. And the top two deal mostly with academic research, both outreach and engagement, and also providing ARM IP to facilitate research that's going on out there. ARM education is looking at more computer engineering and STEM skills gaps and trying to provide materials to the education sector to help with that. Okay, so I spent a bit more talking about, first of all, the education, collaboration, and enablement. From the education group, they have three activities. So there's the university program, which is free access to everyone, rigorous education kits looking at the electrical, electronic, computer engineering, computer science curricula. So that's available to all, and the kind of premium version of that, if you like, is education media, which then looks to provide more rich multimedia content, digital first books, and that is available to all. So not just universities, but anybody that would like to be skilled up in a different area, would like to have the materials available to them. That's the ARM education media. And finally, we recently set up an ARM school program, which is taking the mold, if you like, of the university program, but applying it more to pre-college, pre-university education. So that's ARM education. If I then move on to collaboration, so they are like the frontline interface between ARM research and universities. So we have the two directors present here today. Rafaela leads the US, and I can't see Andrea, but if you can stand up and wave, that would be awesome too. Hi, Andrea. So these guys are in the room and will be present at the summit. Their main aim is to help make connections and kind of support and facilitate engagement between ARM research and kind of academic institutions out there. So why would you want to work with us? So it's kind of similar reason why a lot of the corporate folk do. And I think to sum it up, it's really risk reduction. So we have a wide portfolio of IP tools and software stacks that are kind of battle-hardened, have been tested. Lots of people have worked together to find the issues with them and fix them. So there's a very vibrant ecosystem out there of both baseline technologies and also partners that you could work with to bring together technologies and tape out your research ideas. This network of kind of academic and research is very large, so I'm sure this is a spot who's missing, and we'll work on this over time to keep it up to date. But we have activities with all the guys on the slide here. Some of it is kind of closer, tight-knit research between, so the ARM research programs function and some academics outside. Other stuff is related to providing IP to facilitate the research that they're doing. And other things looking at potentially some of the funded projects that are going on and available from the government funding bodies. So I guess as an example of the power of what we could do as a team and working together is ARM's experience in HPC. So I forget when this first started. I might need to point at either Nigel or Eric VH, but I feel it was at least 10 years ago. And in the ARM research management, there was an awesome plan of, well, our processors are pretty low power. What if we scaled them up the number of them? Could we get into HPC? And that kind of amounted to the strategy at the time. We ultimately hired Eric VH, and he came up with a more thoughtful and articulated plan of, hey, let's find out what the technology gaps are. Let's try and close some of those. So be they in the computer architecture or the software tools and libraries that are important to this space. let's engage with the end customers, so the government labs and universities, groups who are active in HPC, and actually look at the workloads instead of representative benchmarks. And let's kind of build up the simulation capability that we have to start modeling those workloads on top of ARM systems. Finally, there's a great amount of activity working with partners in the industry, trying to understand what gaps needed closing there. So that's been a long play activity within ARM research and ARM and its ecosystem. And if you kind of look at today, we did pretty good. So I haven't got everybody represented here, but yeah, this is from nothing, from kind of brainchild and computer simulation. We now have some really compelling systems available out there. So well done. Moving on, talk about ARM research enablement. So we have a long record actually at ARM of providing our IP to academics to do, basically to enable their research in whatever way they would like. So some of this is altruistic in that, you know, research generally is a good thing to enable out in academia. Some of it is more self-interested of, well, if you come up with the next ML or whatever on top of ARM technologies, that could be good for us as a business. But fundamentally, we're interested in getting IP available to any academics for their research purposes. And I think 4 years ago, ARM Research picked up the company's owning of enablement for academia. And since then, we've been increasing the kind of professionalism and the experience that you should get. So I think if you look at like 2018, we have shipped Cortex-M to something like 700 academics for them to incorporate into their projects, tape out either to FPGA or silicon. Something like 100 instances of the ARM physical IP library has also been sent out to academia. So moving forward, we're looking to kind of improve that experience for academics, so not move beyond, say, the restricted set of technologies available under Design Start. But essentially, I think the message to academia is if there's any ARM IP that we could make available to you, that's what we would like to do. Going to be working heavily on improving the experience of working with us and the legals, and also the kind of last bullet in the building academic ecosystem there is figuring out ways that we can enable academics to work together based on top of ARM technologies, because I understand that's been a legal agreement blocker in the past. So tomorrow, Plute will be leading a workshop on research enabled by ARM. If you're interested, I encourage you to turn up to that. One of the things he'll be talking about there is the ARM Flexible Access program for research. You may have seen in the press recently, ARM Flexible Access was announced for corporate or commercial players, providing easier, cheaper initial access to IP. So the ARM Flexible Access for research is doing something similar for academia, much wider range of IP available and a much more streamlined sign-up, approval, and legal process. So we're launching it initially this year with a small group of academia with a plan to launch that more aggressively early 2020. Okay, so that was the kind of external-facing function of research. I'm going to talk now a little bit about research programs. And this is a slide which talks about kind of our focuses, and it kind of splits into two. So ARM Everywhere and is essentially addressing and looking for technology solutions for the hardware IP side of the business, and the value from data is looking at fundamental technologies that we could deliver to the IoT services group within ARM. So for ARM Everywhere, essentially if we look at the different business activities of ARM the company, there are about 3 lines of businesses, so large commercial sectors that we're interested in as a company. And from there, research programs internally is trying to figure out, okay, at what point in the future should we be aiming for? What technology problems does that suggest? And what research projects do we charter to try and close those gaps? And some of those research projects will be internal, some may be not our speciality area or a little bit too far out in time. And that might then lead us to work with the collaboration team to work out what our engagement opportunity is. Other things for ARM Everywhere, if you think about new, better architecture for be it client or automotive or infrastructure, IP, maybe looking at what new process technologies are coming along. So we're pretty successful in the CMOS dominated space. We can see potential market segments like printed electronics or low temperature electronics. And part of the remit of ARM research internally for the program is to figure out how do we secure the right of the company to play in those spaces in the future. It may be we decide commercially not to because we don't see enough money, but from researchers' point of view, we need to figure out, okay, what technology gaps need closing? Let's figure out are there solutions to those so that there are no impediments for the company should they choose to execute there. So from the value on data on the right-hand side, there's a lot of interest there in making sure that we can scale up the management of the Internet of Things, of many, many devices, getting the connectivity, getting the security, and ensuring that the flow of data from the endpoints back to the cloud is appropriate in volume. So I'll run through a couple of projects which are somewhat linked. This chart is from the commercial side, so I've borrowed a slide from a deck somewhere. The only message really from this I take away is if the Internet of Things pans out, then the flow of data is in the opposite direction to the way the Internet was designed. So for that to actually work, we need to put a lot more intelligence on the left-hand side. Capture data, yes, but process it, evaluate it, and minimize the amount of data which is being sent back to the cloud for processing. So I come on to the endpoint initially. We see, certainly if you're going to be scaling up the number of devices at the edge, an awful lot of them may not have kind of mains power access. So to that end, low energy, efficient, wireless connected devices are a really important factor in our thinking. Mono I did speak about last year at the summit as well. Since then, I don't know if James's team has had 2 or more tape outs, all successful. But there's been a great kind of iterative system co-design going on. So the box in orange, for those unfamiliar with Mono, is the bit with the kind of near threshold smarts to it. So that's operating in active mode between 0.4 and 0.8 volts on 65 nanometer process. Around it, the blue section is a really stripped down, always on component, which is there to wake up the power supply to the kind of active-only processing domain. And then the gray box is really there for co-development in the experimental platform. So I think over time we started off on M0. Latest tape out has got Cortex M33, which is really good for kind of edge point ML processing, some DSP assist in that instance of the Cortex M. So from the last tape out, got pretty world-leading kind of low shutdown power and active energy compared to commercial off-the-shelf MCUs. Also been showing it downstairs with some tiny ML keyword spotting algorithms running on it. And it can run for many days on a tiny coin cell. So it's a really successful output from the project. Mono on the PCB there is the kind of lower center IC and a couple of passives. The other stuff, I guess, is for the demo and code development. Okay. Moving away from Mono for a minute, I'll come back to it. It's great to have excellent energy efficiency at the endpoint, excellent to have awesome ML experience. But if the endpoints are not secured well, then yeah, they're vulnerable to attack, and you may not be trusting the data that you're collecting from them. So a long line of projects of engagement that we've had, certainly with ARM overall and ARM research, to the University of Cambridge work on Cherry, which is a compartmentalization and capability model that they've been researching for a number of years now. We're running a project in programs which is evaluating how would that technology look under microcontrollers. So for those not familiar with Cherry, it's mostly looked at application domain processors with rich software stacks running on top of them. So you're going from a proposition of, okay, we have a 64-bit architecture, and under the proposal from the Cherry group, you'd expand registers that are storing addresses to 128 bits. You can then start getting some base and bounds of the objects that they're referring to. So the key thing with the capabilities technology is yeah, they appreciate that an awful lot of the compromises and issues caused in software stacks are the confusion between data and a reference to a place in memory. So the portions of the technology being proposed there hopefully at a very high level raise the bar to say, well, no, actually you can't corrupt memory and adjust addresses anymore. If you do a data write, then the memory system will know that that's actually data and it cannot ever be used as an address reference. So anyway, we're looking at, for a much smaller implementation, so with a 32-bit register file, what are the options for picking up the inspiration from the Cherry model for application calls? What does that mean? So that's an ongoing work. So moving back again to feature mono, so the keyword spotting algorithm in the demo downstairs has been making use of some of the tiny ML kernels that the ML group in research have been looking at. And the focus there is, if it's important to do a lot of processing at the edge of the network, a lot of the systems there will be constrained both in energy availability, both in performance and also memory available. So the group is very interested in what can we do to take the trained models that you may have put together under a GPU in the cloud, take those trained models, but then specialize them for the really limited constraints of microcontrollers and wireless sensor nodes. So next slide is an example of that. I won't butcher the technology work behind it, but essentially the DSCNN was the baseline. That's the red dot on the charts. And through clever application of maths and rearrangement of data is what I describe it to, they managed to get pretty impressive improvements in memory footprint and operations needed. So the group actually has many of these activities, many different optimization techniques, many different ML models that they're working on. And as you put all those together, it may be that for a specific application, one particular model, one particular grouping of settings is the appropriate one for your problem, which then turns itself into an application development issue for the programmer. So the obvious thing to do at that point is to automate the search. So Autobot is another project that they have running, which is looking at a neural architecture search to figure out for your particular domain, your particular task, what's the best model, what's the best set of configuration options that are going to give you the best kind of performance, memory footprint, and minimize the error compared to kind of the ideal at the unconstrained implementation point. Okay, if we move on to an example that's coming out of our more services focused research. So we spoke through, you might have a mono, it may be in one place in the geography. You may have lots of those, and you may over time have updates to the keyword spotting in that example that you would like to apply. So the information or IoT services focused research at ARM has come up with some systems based on Kubernetes where you can get essentially modern application management for the edge compute. So you can come up with a new improved model and deploy it seamlessly out across your network and get that updated. Okay, so that was a quick run through of some projects that we have. The scope of the areas that the research programs are interested in is much broader than that. There are some examples here, but yeah, we kind of touch the stack from where are materials going all the way up to what are the software systems running on top of that. So if that's of interest to you, there are vacancies available both in research and wider ARM. So whether you're interested yourself or you have students who may be interested, we run a big internship program every year in the US and the UK, and there are a number of established places available also. So follow up on the links if you are interested. And with that, I've ripped through the slides pretty quickly, so some closing remarks. Thank you for coming and listening this morning. I think to me, what I've really appreciated at the ARM Research Summit over the years is, I guess my background is processor architecture, and I like going to architecture conferences and getting the deep dives into topics that excite me. What I found interesting from the summit over the years is the breadth and the areas that I've got no idea about, yet people have made a good effort to describe it to lay people. So you can take something away and from that perhaps make the connections of, okay, so their problem's a little bit like this. I in my domain, might be able to work to help them and close that gap. So together, we may do great things. So with that, I think I'm done.